Hi, everyone. Today's our second lesson. I'm waiting for one more student to join, but I'm going to start the class anyways. And hopefully when this student joins in, we can just admit her and carry on. All right, so actually, I only received a key question from Judy. I haven't received any key questions from anybody else.
Oh, sorry, I'm gonna send it right now. I forgot to send the email.
Okay, thank you. How about you, Sasan?
Oh, that was me that I just said.
Oh, sorry, Borna?
Miss, I had a question. So
Yes.
you told me to just do question 3, or was I supposed to do all 3 of them?
I only needed you to do question 3, but if for
Okay,
your
yeah.
own practice you wanted to do all, that's perfectly fine too.
Okay, I'm gonna send it right now. I had it finished. I just
Okay, perfect.
all right.
Okay, in the meantime, does anybody want to go first? All right.
I can go first. I'll just find it. Give me a sec.
For sure.
Okay, so this is for 3A. So spectroscopy is, yeah, mine is. Oh, I think I did the wrong question, miss. I answered.
Yeah,
what
you were
is
assigned number
spectroscopy?
1.
Oh, I thought it was assigned 3. I finished 3.
Okay, all right.
I can do 1 really quick.
All right, sure. Maybe we can take this question up next class with you. How about that?
All right, sorry
Okay.
about that, miss.
No worries.
I can like share my answer after Sasan if you want.
That's okay. I mean, just spend the time listening to Sasan and participating in class. You can always, I'll allow you to do this next class.
All right, thanks.
Okay, no worries. All right, Judy or Sasan, do one of you want to go next? Maybe Judy, since that's question number 2.
Yeah, I can go.
Sure.
So my question was, explain the main weakness with Rutherford model of the atom and how Bohr addressed it. So I said the main weakness with the Rutherford model of the atom is that he did not succeed in discovering the discontinuous nature of hydrogen spectra, while Bohr's model discovered the line spectrum of hydrogen and showed how the electrons configured around the nucleus.
Yeah, so yeah, that's a good answer. So a very good complete way to answer that is actually there's 2 weaknesses to Rutherford's model. One of them was definitely the one you said, that it did not explain the emission spectrum of hydrogen, and it didn't explain the discontinuous nature of that spectrum. But the other one that probably would be the main weakness is that it didn't explain the stability of atoms. So the problem with his model was that according to the laws of classical physics, as it was understood at the time, you would predict that electrons that were orbiting in this circular way around the nucleus, around in the atom, they would, as they emit energy, they would lose energy and they would spiral. They would lose their energy and they would spiral into the nucleus as they're accelerating around the nucleus. But that's not what was observed. Generally, most atoms are very stable and they don't seem to be collapsing into themselves, and the electrons aren't collapsing into the nucleus, and they seem to be very stable. So Rutherford's model did not explain this stability of atoms, but also, yes, you're right, it also did not explain the emission spectrum of hydrogen. And then, so then the next part was, how did Bohr address it? Well, Bohr made a very big assumption using Max Planck's explanation for black body radiation. If you remember, we talked about how Max Planck understood that energy was quantized. So this idea of a quanta of energy. And so Niels Bohr applied that idea to his atomic model. And he also used the emission spectrum of hydrogen to develop this quantum model for the hydrogen atom, where the electrons of the hydrogen atom moved about the nucleus in a circular orbit. And then you had orbits of different radii, that these different radii correspond to different energies that were permissible because energy is quantized. And then the electrons in these orbits were said to be in their allowed energy states. And in these allowed energy states, these electrons would not spiral downward toward the nucleus. And so that is how Niels Bohr addressed it. He addressed it by realizing that the classical laws of physics did not apply, and that he used Max Planck's idea of quantized energy, and he used quantum mechanics to apply to come up with a model of the atom. Okay, so that was a very complete way of answering that question. Okay, so now let's see. So Sasan, have you got your question?
Yes.
Okay, so spectroscopy.
Yeah, mine is spectroscopy is about the interaction that, wait, oh yeah, my mic is on, sorry.
No,
That
no,
happens,
we could hear you. We could hear you.
okay. That happens between matter and radiated energy. In the past, spectroscopy started with the study of taking visible light and spreading it using a prism to get different colors based off the wavelength. And then the spectroscopy was used to the development of early atomic theory because of Bohr used this and got the spectroscopy of hydrogen, which then he used for developing a model of this hydrogen atom that includes electrons that have different energies, which then he said that there is excited electrons changing orbits because of them getting a lot of energy that will create these colors.
Okay, yeah, that was a good answer. So, and if you like, we can just quickly revisit that slide we had about spectroscopy. And so, yeah, this is what you were talking about. This is spectroscopy. It's analysis of these spectra that various types of atoms or matter or even solutions they can produce. If you pass light through them and pass it through a prism, you get their spectrum, and that spectrum has indications of the characteristics and the features of what was your sample. If in your sample there is it's just solid white light, then you will see the full continuous spectrum with all the colors of the rainbow, essentially. But say if your sample is a pure element, for example, here, like you said, the hydrogen gas. In this case, when the hydrogen gas emitted light and it was passed through a prism, it didn't produce a continuous spectrum. It produced a very discrete lines at very specific wavelengths. And this was true for all different elements, and they all have their own unique line spectrums that is almost like a fingerprint of these different elements. And yeah, and that is exactly Bohr's model incorporated this line emission spectrum of the hydrogen atom and developed the quantum model for the hydrogen atom, where energy is quantized. The energy of the electrons are quantized. They're not allowed to be at anywhere in between. They have to be at very specific energies. Okay, that's perfect. Okay, so we can, so that was our first lesson. Did anybody have any questions before we go on to our second lesson? Was there anything from the first lesson that you felt like maybe you would like me to cover and to go over again and explain again? Everybody good?
Yes.
Okay, perfect. All right, so our next lesson, we're continuing with the model of the atom, and our next lesson focuses on quantum mechanics. And so quantum mechanics versus classical mechanics. So quantum mechanics is that branch of physics that studies the motion at atomic level, where the laws of classical mechanics do not apply because these particles at the atomic level behave like waves. They have wave-like properties. Versus in classical mechanics, it's that branch of physics that studies the motion of macroscopic objects, a ball rolling, a car driving, somebody running, something falling. It's not at the atomic level. And so the development of the Bohr model, which we discussed in the last class, led to further studies of the quantum mechanical model of the atom. And so although this quantum mechanics is a very complex subject in chemistry, we will cover some fundamental concepts to give you a good basis for quantum mechanics. And what you will learn in this lesson is you will learn how to describe the quantum mechanical model of the atom in terms of orbitals, electron probability densities, and also the contribution of important physicists to this model is Planck, de Broglie, Einstein, Heisenberg, and Schrödinger. You will be able to list the characteristics of S, P, D, and F blocks of the elements and explain how their relationship between where they are on the periodic table, their properties, and their electron configurations. And you will be able to write these electron configurations for elements on the periodic table using Pauli's exclusion principle and Hund's rule. So those are the things we'll be covering here. So now to just quickly recap so that we can very fluently go into quantum mechanics, we left off our discussion of the atomic model. So after Rutherford discovered the nucleus of the atom, as you recall, scientists were really tempted to think of the atom as this microscopic solar system where electrons would orbit around the nucleus in circular paths called shells, sort of like planets going around the sun. The problem with that model was that according to the laws of classical physics, which was what was understood at the time of that model, Rutherford's model, was that one would predict that these electrons would just continuously lose energy and spiral down towards the nucleus. But this prediction was not supported by observations and experimental evidence. Generally, most atoms were very stable and were not collapsing. So Rutherford's model was not able to explain the stability of atoms. Now, if you recall, the Danish physicist Niels Bohr, he solved this problem the same way that Max Planck had solved the problem with black body radiation. They both made the assumption that classical physics was inadequate to describe their problem. Niels Bohr assumed that the emission spectrum of hydrogen could be addressed using Bohr's assumption, using Planck's assumptions. And he used the emission spectrum of hydrogen to develop a quantum model for the hydrogen atom. And he proposed in his model that, first of all, the electrons of the hydrogen atom moved about the nucleus in a circular orbit, but only orbits of certain radii corresponding to certain allowed energies were permitted. And when you had an electron in a permitted orbit, it's said to be in an allowed energy state, and that electrons in these allowed energy states would not be spiraling towards the nucleus. The second thing he proposed in his model was that these electrons could change from one allowed energy state to another one by absorbing or emitting radiant energy. And the frequency of this energy had to correspond exactly to the energy difference between the allowed states. So Bohr's model was important because it had the idea that electron energies were quantized. And Bohr's model initially looked very promising. For example, these electron energies that were predicted by Bohr's model were very similar to the values obtained from the emission spectrum of the hydrogen atom, as we said. But by the mid-1920s, scientists could see that Bohr's model had its shortcomings. It had its limitations. It couldn't explain and make any predictions about electron energies in multi-electron atoms. So Bohr's model could not fully describe the structure of an atom, and it was eventually replaced by a new way of viewing atoms. So, and there are three physicists who were key to understanding of this new approach were Louis de Broglie, Erwin Schrödinger, and Werner Heisenberg. And the approach that they developed to explaining the properties of matter here is called wave mechanics, or more commonly, quantum mechanics. And this new physics did a better job, more accurately explained the behavior of light and matter, and it was a crucial piece to our understanding of the modern day atomic theory. So let's talk about what were the ideas of these three physicists, and then we can get further into the modern atomic model. So de Broglie in 1924, so for the years that kind of came after Bohr's model, the dual nature of radiant energy was a familiar concept. And everybody, most scientists agreed that depending on the experimental circumstances, radiation could have either wave-like properties or particle-like properties. So what Louis de Broglie, who was actually a French student who was working on his PhD, he just decided to extend that idea that if radiant energy under appropriate conditions could behave as though it were a stream of particles, wouldn't matter also under the appropriate conditions be able to show properties of a wave? So he made the assumption that an electron has wave-like properties and it has a wavelength. And he proposed that the wavelength of the electron or of any other particle is dependent on its mass and its velocity. And that is given by this equation where lambda is the wavelength, h is Planck's constant, m is the mass, and v is the velocity. But so the problem is that a wave kind of extends into its space. Its location is not well defined. How can we, at any given moment, calculate exactly the position, the direction, and the speed of an electron that has wave properties? How are we going to do that? That was a problem that was a question that many people were asking, many scientists were asking and looking for ways to answer that question. So then Schrödinger, an Austrian physicist, decided to approach the problem of atomic structure by focusing on the wave properties of the electron, like de Broglie had proposed, and proposed an equation that is known as the Schrödinger wave equation. And this equation produces a series of solutions called wave functions. We're not going to get into that. It is a far too complex area of quantum chemistry for the levels that we are at in this course. But just to give you an idea, the wave functions are usually represented by the symbol of this dagger symbol called psi. And although this psi itself directly doesn't have any physical representation, but the square of this wave function, so psi squared, does give information about the location of the electron when it is in its allowed energy state. So in this led to the idea that these allowed energy states were the same as those predicted by the Bohr model, but the Bohr model had electrons in a circular orbit around some particular radius, some distance away from the nucleus, whereas this quantum mechanical model, we can speak in terms of the probability that an electron will be in a certain region of space at a given time. And this region in space is called the electron cloud, and it has the probability density for an electron, for example, in a hydrogen atom. So we can't really speak about exactly where. We can talk about what's the probability that we might find the electron somewhere in this electron cloud. And so the best we can really do is to describe the probability of finding an electron in a specific location. The other thing I want to just touch on here is that these Bohr-Rutherford diagrams are widely recognized, are useful, but they are not an accurate depiction of what is actually happening inside of the atom. And sometimes, although we use these extensively in chemistry, it's easy to forget that according to our current theories of quantum mechanical theories, model of the atom, electrons don't actually orbit around the nucleus. They don't actually orbit around the nucleus. So it's more of a probability of where they are around the nucleus. So finally, in 1927, a couple of years after Louis de Broglie had his hypothesis and Erwin Schrödinger made his contribution, a scientist called Werner Heisenberg, who was actually doing his postdoctoral training with Niels Bohr at the time, he came up with a statistical approach for locating electrons. And so in order to measure the location and speed of any object, you must be able to observe it. But for atomic sized particles and anything small, at that scale, any attempts to probe them to find out information about their location or their speed changes that property, changes the position and the direction of the travel, or both. And this was the idea that formed the basis for Heisenberg's famous uncertainty principle. And he got a Nobel Prize for this. He was the youngest scientist at 32 years to receive a Nobel Prize at the time. And his idea, his uncertainty principle, stated that it is impossible to simultaneously know both the exact position and speed of an electron at any given instant. So de Broglie's hypothesis and Heisenberg's uncertainty principle really came together and set the stage for a new and more widely applicable theory of atomic structure. And in this new approach, we think of the wave-like nature of the electron, and we give up the idea of trying to define a precise location and momentum for the electron at any given instant. It is understood that there's a probability of where the electron may be found at any given time, that there won't be any precise location. So that idea of trying to define a precise location or a precise speed or momentum of the electron was completely abandoned under this new approach, while assuming a wave-like nature for the electron. So now I want to talk about these orbitals and these probability distributions. And I just want to compare and contrast the idea of orbits and orbitals. So in the Bohr model, you had a single quantum number, n, if you recall, that described the orbit. So n is equal to would be the orbit at the lowest energy state, n is equal to 1, n is equal to 2, n is equal to 3 and 4, so on and so forth. And these orbits or shells or energy levels were depicted by n is equal to 1 or k, L, and M were other ways of talking about it. Now, in the quantum mechanical model, there are more numbers that define these orbitals, and orbits and orbitals are not the same thing at all in chemistry. In quantum mechanical model, you have 4 numbers, n, which is the same as the n in the Bohr model, the principal quantum number. You have another value called L. You have m subscript L and m subscript S. And these 4 numbers together describe an orbital. So in the quantum mechanical model, each electron can be described by a set of 4 numbers called quantum numbers, and no 2 electrons in the same atom can have the same set of quantum numbers. It's unique for each electron. And these orbitals are defined as regions where electrons are most likely to be found. So again, the idea of a statistical approach, a probability density. So in this picture, I've tried to represent an overlapping of the different orbitals in around the nucleus of an atom. And as you can see, they are not these round orbits, these circular round orbits or shells that Bohr had described in his atom. Rather, each one of them has a specific shape and a directionality to it, and they do overlap. So let's talk a little bit more about how do we arrive at these numbers and how can these numbers be used together. So, right, in this chart here, again, I summarize sort of the difference between orbitals and orbits. In orbitals, in each orbital, you can have up to 2 electrons, whereas in the orbits, you could have 2n squared electrons. So in the first shell, n is equal to 1, you would have 2 electrons. In the second shell, n is equal to 2, you would have 8 electrons, and so on and so forth. And in the orbital of the quantum mechanical model, the distance of the electron from the nucleus varies. It's just a probability. It's an electron cloud. It could be anywhere in here with sort of the probability getting less as you're farther away and maybe more as you're centered towards, sort of depicted by this haze over here. In Bohr's model of the orbit, the distance from the nucleus was fixed. You're either here or you're here, but you're somewhere along that track. Somewhere in that shell you are, but you're either here or here. You're fixed distance from the nucleus. And in the quantum mechanical model, there's no set path, whereas in Bohr's model, the paths were set. They were elliptical or circular, but it was set. Now, in the quantum model, for every value of n, the principal quantum number, there are n types of orbitals and n squared actual orbitals. What do we mean by that? So, so here we can look at sort of these 2 first values, which you recall were from the initial, the Bohr model. So n is equal to 1, the principal quantum number, 1, 2, 3, 4, so on. And they had the symbol K, L, and M. And in each one of these, they had a number of subshells. So in the K or energy level, and the n is equal to 1 energy level, you would have 1 type of subshell. In the next one, n is equal to, there would be 2 types of subshells. And in 3, there would be 3 types of subshells. And in 4, there would be 4 types of subshells. And then you would have a maximum number of electrons for each of these shells. And and a maximum number of electrons for each of the subshells. So here, let's go through the example of, actually, let me come back to this slide. Maybe I should go and first talk to you a little bit more about the principal quantum number, so that n. So this principal quantum number, as we were talking, can have these values of 1, 2, 3, 4, and so on and so forth. And as n increases in value, it means that your orbital becomes larger, and that the electron is able to spend more time farther away from the nucleus as the orbital is getting larger, and it can have higher energy, and it can become less tightly bound to the nucleus. When you have a collection of orbitals with the same value of n, so if they all have a value of n is equal to 1 or as n is equal to 2, if they all have the same value of n, this is called an electron shell. Now the shell is further subdivided into subshells, and the number of subshells equals the principal quantum number. For example, n is equal to 3, then that tells you that you have also 3 subshells. Now the second quantum number, L. The second quantum number can have values that range from 0 to n-1. It turns out that to fully designate all these possible energy levels and the probability patterns, we have to modify the atomic model by subdividing each shell or each of the orbits into a number of subshells as the principal quantum number goes up. So this is not true, for example, for the first shell, where the principal quantum number is 1. There's only one shell. There's no other subshells. It's just 1. And this was introduced by a scientist called Arnold Sommerfeld in 1915, and he used this idea to explain line splitting of the hydrogen spectrum. So the secondary quantum number identifies electron subshells or sublevels of the main energy level, and also the shape of the orbit. I'll describe this in more detail as we get further into our lessons. So by line splitting, yeah, he could see that there was these in the energy level diagram, that these lines were at each energy level, it was split into more finer energy levels of different values. So a second quantum number was devised that would have a value of anywhere between 0 to n-1. And if the value of L was equal to 0, then it was given, designated as an S subshell. And the S and the P and the D and the F actually have meanings, sharp, and I forget what else, diffuse, and anyhow, but they're known as S, P, D, and F, depending on the value of L. So if L is equal to 2, then it's referred to as a D subshell or D sublevel. So the letters S, P, and D, and F correspond to these values of L. So for example, if you have n is equal to 1, as we have here at this level of the energy diagram, then there is only one sublevel, and L is equal to 0. And the subshell is designated 1 because it's n is equal to 1, S. And that's because L is equal to 0. At n is equal to 2, then there are two sublevels. So an L can have a value of 0, and there can be an L of value 1. See, 2 types of sublevels. And then there are designated as 2 because it's coming from the n is equal to 2 energy level as 2s because L is equal to 0, 2s, S is for L is equal to 0, and then 2p. When L is equal to 1, it's a P sublevel, subshell. So these at n is equal to 2, you would have 2 sublevels. You would have an n is equal to 2, we would have a 2s and a 2p. And as you can see, that's how the pattern continues. When n is equal to 3 at this energy level, you will have 3 sublevels. The value of L can be 0, will be 1, and will be 2. And 0 corresponds to S, 1 corresponds to P, and 2 corresponds to D. So instead of calling it sort of a 3, 0, 3, 1, they call it a 3S, 3P, 3D, just to make it more clear. So all of the orbitals of an atom, for example, with an n is equal to 3 shell and L is equal to 1, for example, over here, would be collectively referred to as the 3p orbitals, or the 3p subshell. So that's the language that we're going to be using to talk about these orbitals and subshells. There's a support question here to give you a bit more practice working on this. Then there was another quantum number, the third quantum number, called the magnetic quantum number. And the magnetic quantum number has whole number values between value of -L and +L, including 0. So for example, if here you're looking at L is equal to 1 in the 2p orbital, for example, so then it can be further split into further 3 lines of ML is equal to -1, 0, and 1. So if you think back to the line spectrum and how it was created by passing electricity through a gaseous element, and then the light is passed through a slit, through a prism, and you get this line spectrum of the element. Now, if you take this gas discharge tube, like the one that we had when we, for example, looked at the hydrogen line spectrum, I'll show you. Yeah, remember this diagram? So if we take that discharge tube and we put it near a strong magnet, then some of these single lines split into new lines that were not initially present. This effect was discovered by Peter Zeeman, and it's called the Zeeman effect. And he observed that a single line could transform into 3 lines when a magnet was applied. And this was termed the Zeeman effect, and the magnetic quantum number was used to describe the splitting as the orientation of these orbitals in space relative to other orbitals in the atom and in the directions of X, Y, and Z. These are the 3-dimensional coordinates that you refer to when you're describing something in 3 dimensions, in the X-axis, Y-axis, and Z-axis. So this was the orientation of these orbitals relative to the external magnetic field. So let's go through an example here. So for example, when L is equal to 1, then you would have 3 possible orbitals, because you could have values between -L and +L, including 0. So here L is equal to 1, so you can have values between +1 and -1, including 0. So these 3 types of orbitals would be called all p orbitals, because they all have L is equal to 1. And if you remember from our chart over here, when L is equal to 1, we designate it as a p orbital. But they're different from each other because of their orientation. So these 3p orbitals are differently oriented with respect to each other in space. So if you think about your XYZ coordinate system, the number of the different values that this ML can have equals the number of orbitals that are possible. And for every value of n, there would be n types of orbitals and n squared actual orbitals. So during in your first energy level, where n is equal to 1, this energy level would have one type of orbital and one actual orbital. So one type, and how many of it? 1. In the second energy level, you would have 2 types, and how many of those? 4 altogether. In the third energy level, you would have 3 types, and how many of those 3 types? You would have 9 orbitals. And we will definitely cover these things more in more slides as we go down, as we go further into our lesson. So finally, let's talk about the 4th quantum number. This one is called m subscript s, the spin quantum number. The spin quantum number can have value of plus and minus 1. So when scientists were studying the line spectrum of multi-electron atoms in greater detail, they noticed that the lines that were originally thought to be single were actually closely spaced doubles. They were in pairs, essentially meaning there were twice as many energy levels as they were supposed to be. And so 2 scientists, Uhlenbeck and Goudsmit, they proposed that electrons have this intrinsic property called electron spin. And this electron spin, ms, m subscript s, would have the values of either +0.5 or -0.5. And this would indicate 2 opposite directions that an electron can spin. Electron can be spin up or spin down, plus and minus, respectively. And that a spinning charge produced a magnetic field, and therefore these 2 oppositely directed magnetic fields led to the splitting of these spectral lines into closely spaced pairs. So atoms have their own magnetism, which is unique to the magnetism of that group of atoms. And this magnetism is referred to as paramagnetism. And you can, we will get into this possibly later on in the course, the idea of paramagnetism. Right now, don't have to worry about it much. And so these electrons spin on their own axis. So if you can picture an electron spinning about its own axis, in either a clockwise orientation or a counterclockwise orientation. So either with a spin up or a spin down, given the values plus and -0.5 respectively. And it was the Austrian physicist Wolfgang Pauli that discovered the principle that governs the arrangement of these electrons in multi-electron atoms. And this led to Pauli's exclusion principle. Pauli's exclusion principle states that, let's highlight this because this is important, that no 2 electrons in an atom can have the same set of 4 quantum numbers. They can't have the same set of N, L, ML, and S, that any 2 electrons will have their own unique set. And that an orbital can hold a maximum of 2 electrons. And these 2 electrons must have opposite spins. One of them must be pointing up, one of them must be spinning down. Up spin, down spin, or would have the value of +0.5 and -0.5 for the ms. So for example, you can have 2 electrons having the same N, having the same L, having the same ML, but they cannot have the same ms. One of them would have to be the +0.5 and one of them would be the -0.5. So no 2 electrons could have the same set of 4 quantum numbers. So let's actually go back to that slide where we were talking about. So here in this diagram, this is a good diagram that shows, for example, the energy levels of each one of these shells. So when n is equal to 1, the energy level, for example, would be here. and you would have one type of orbital. You would have the s orbital because n is equal to 1 and L is equal to 0, which would make it an s orbital, and you would have just that. You cannot have any other kinds of orbital. You can't have p orbitals or d orbitals at the n is equal to 1 energy level. When n is equal to 2, so if we can follow along here on this table, so when n is equal to 2, you could have 2 subshells. So here n is equal to 2, and we have 2 subshells. We have the s and we have the p. So you can have the 2s and the 2p. You have 2 types of subshells. And in these types of subshells, you would have the 1, and here you would have 3 corresponding to your L is equal to 0 and your L is equal to -1, +1, and 0. And each one of these would have could occupy 2 electrons with their spins pointing in opposite directions. So you could have 2 electrons occupying this orbital, 2 electrons here, 2 here, and 2 here. So 2 plus 2, 4, 6. So you could have a maximum number of 2 plus 6 or 8 electrons altogether at this energy level where n is equal to 2, and according to this energy diagram. And we can look at this also at the n is equal to 3 energy level, and n is equal to 3, you would have 3 types of orbitals and 3 squared orbitals. So see 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 squared is equal to 9. You have 9 orbitals of 3 types. You have 1 of the s, you have 3 of the p, and you have 5 of the d type orbital. And each can contain 2 electrons. So you could have 2 electrons in your 3s orbital. See, 2. You could have 6 electrons in your 3p orbitals. So 2, 4, 6. Okay, there's your 6. And you can have 10 electrons in your d orbital because there's 5 of them. 2, 4, 6, 8, 10. Altogether, at this energy level, you could have 18 electrons, or 2n squared. So 3 squared is 9 times 2 is 18. You could have 18 electrons at this level, 2 in each orbital. Yeah, so that does that slide for me. So again, we keep going back and forth and contrasting and comparing Bohr's atomic model to the quantum model. So the early Bohr model was based on the idea of the electron traveling in a circular path or an orbit. But we know that this modern day theory is that of an electron orbital. And orbital is just a volume of space where an electron is most likely to be found. And these are some probability profiles of, for example, a 2s orbital would have this kind of a probability profile. So there's high probability to find the electron here and there, and then low probability where it looks lighter and more sparse. Here is a probability profile for a 2p orbital. It kind of has like a dumbbell shaped with like a node in the middle. So it'd be a probability of finding electrons here, sort of higher in this denser region, and less probability further away from the center, from the node. So quantum mechanics was built on the earlier idea that electrons within an atom can possess only discrete quantities of energy. And that was Bohr's contribution. He took Max Planck's idea of quantized energies, and he applied it to the atomic model of the hydrogen atom. And from there came the idea that electrons possess only discrete quantities of energy. And quantum mechanics retains this concept that electrons fill successive energy shells, each of which is designated by the principal quantum number, as we went through, and that the two principal quantum numbers N and L describe electrons that have different energies under normal circumstances in multi-electron atoms. Now, what do I mean by normal? I say normal as opposed to abnormal, which is where the other two quantum numbers come. The other two quantum numbers were only discovered because of sort of abnormal conditions, sort of under application of a magnetic field. That's when those two were discovered. So we will focus on energy shells, the principal quantum number N, the primary quantum number, principal quantum number, and we will focus on subshells, L, or the secondary quantum number. And we will communicate these values of L with the letters, so not to get confused, and rather than the numbers. So again, I think I showed you this table before. When L is equal to 0, it's called an s orbital. S is for sharp. I'm not sure exactly historically where these words come from, but that led to S, P, D, and F. And each one of these has a certain number of orbitals associated with it. So if you remember, S orbitals only come in 1s, P orbitals come in 3s, D orbitals come in 5s, and F orbitals come in 7s. So if you can go back to, I was showing you here on this slide, yeah. So S orbitals come in 1s, see, S orbitals come in 1s, P orbitals come in 3s, and D orbitals come in 5s, and F orbitals, which is the next energy level up here, would come in 7s. And I have a table here, which I've just gone, I got this actually from your textbook. The only thing is I added this, this column with spin number in it that shows for each one of these, you would have 2, the number of electrons in each energy density. So at N is equal to 1, you would have a L is equal to 0, which would be an 1s sublevel designation. And you would have 2 electrons here because one of them would be plus half, one of them would be minus half, spin up, spin down, 2 electrons. And so on and so forth. You can go through this table and see and understand how there's different orbitals. The number of orbitals, see 2s, there's only one of it. 2 p's comes in 3s. And if each one of these gets 2 electrons in each, then you get a total of 8 electrons at this energy level, 2n squared electrons at that energy level. And so on and so forth. You can go through this table and work through it. So let's talk about the shapes and orientations of these orbitals. It's kind of abstract, but just let's go through it. So the orbitals represent electron probability distributions. And each orbital then has a unique probability distribution, a unique shape, and a unique orientation. So we were talking about the s orbitals. S orbitals are overall spherical in shape. So here I've shown representations of what a 1s orbital might look like, a 2s orbital, 3s orbital, and what you notice here that the orbitals become larger as n increases. Then let's take a look at, and yeah, s orbitals are spherical. So if you look at it on an x, y, z axis, it's kind of got no specific orientation. It's sphere. Now, p orbitals have got 2 lobes. They're kind of like this dumbbelled probability distribution, this kind of a shape. And there are 2 lobes separated by a node at the nucleus. And they can exist in any of the 3-dimensional coordinates that XYZ coordinate system produces. So you can have 3 of them. You could have a p orbital oriented in the x direction, p orbital oriented in the y direction along the y-axis, or p orbital along the z-axis. And that's why you have 3 types of p orbitals. When it's p orbitals, you have 3 types. Now, d orbitals, if you notice, always 3d, 4d, you have 5 types of orbitals. And these d orbitals are shaped something like this. Don't need to worry too much about the details, but these d orbitals you don't have to deal with until n is equal to 3 at that energy level. And at that point, what you have to remember is that you have 5 types of d orbitals, and they have each have their own distinct shape and orientation. This one's a bit funny. But yeah, don't need to go too much into that detail. Next, let's take a look at the energies of these s, p, and d orbitals. So in this panel, on this side is the energy level diagram for what was the hydrogen atom. So in the case of the hydrogen atom, you can see that the subshells within any given shell are all the same energy. So you have just one line here and one energy level here, because even though you have 2s and 2p, they're all the same energy. 3, they're all the same energy. You have 3 different types of orbitals at n is equal to 3, but they just have got the same energy. At n is equal to 4, you have 4 different ones, but they all again have the same. So this is sort of what you would see, what Bohr saw with the hydrogen atom. This was what he based his model on. But in other elements and multi-electron elements, you see that each of these subshells within each given shell have different energies. So at the 1s orbital, well, there's only one, so there it is. At the n is equal to 2, you have 2 orbitals. You have the s and the p, and the s and the p in a multi-electron atom for all other elements other than hydrogen have different energies, and so on and so forth. And the farther you get from the nucleus, so the higher your n number, the farther you're getting from the nucleus, the closer are these energy levels together, and you get an overlap of these subshells because the energy levels just seem to be really close. So let's look at that idea, for example. In this one, again, comparing what would be an energy level diagram for hydrogen versus a typical multi-electron atom, you see that in the hydrogen atom, the 1s orbital would be here. For example, that would be the lowest energy state. And as you get higher energy, your 2s and your 2p are the same, and your 3s, 3p, 3d the same, and your 4s, 4p, 4d, so on and so forth, they're all the same. The message being, in a hydrogen atom, all of these subshells, these orbitals at a given energy level have the same energy. This is not the case for multi-electron atoms. In multi-electron atoms, they have different energy levels. Your 2s and your 2p have different energy levels. In hydrogen, they have the same energy level. Your 3s, 3p, and 3d have different energy levels, whereas in hydrogen, they have the same energy level. In fact, as you can see, the 3d is getting very close to the energy level of the 4s. So these orbital energies are lower in a multi-electron atom. So if you compare even just the 1s of the multi-electron compared to 1s in a hydrogen atom, the orbital energies are lower in a multi-electron atom than in a hydrogen atom. The same is true, for example, for the 2s, 2p. You can see they're lower energy. And in higher number principal shells of a multi-electron atom, so looking at the shells up here, some of the subshells can have almost nearly identical energies. Yeah. So So in our modern atomic theory, it is inferred that electrons in an atom have different energies. Yeah, we just went and discussed in great detail how the energies of electrons can be different. So these electrons can have different energies, and the atomic spectra indicate that the energy sublevels defined by quantum number, and that the energy level diagram shows that the relative energies of the electrons are different, and there you can you represent them in their various orbitals in a diagram like this one, or in a diagram like this one, or in a diagram like this one, for example. And I hope you're all noticing that this one, you should be guessing that corresponds to hydrogen, because your 2s and your 2p, your 3s, 3p, 3d, they're all in the same energy level. If it was a multi-electron atom, these would be in different heights, different levels. So here's another picture of an energy level diagram. And what I want you to notice here again is, again, I'm talking about the same thing, just going through it a different way, is that each electron orbital here in this picture is represented by a circle, and each one of these orbitals can contain 2 electrons. So you can imagine 2 electrons here, 2 here, 2, 2, 2, and so on and so forth. And the energy of these electrons increases with increasing principal quantum number n. So as your number goes up, principal quantum number goes up, so does the energy of these electrons. So the electrons in this portion of the energy level diagram would have higher energy than the electron here, which would be actually, this would be the ground state. This is the first energy level. And that for any given value of n, the sublevels increase in energy in the order of S, P, D, and F. So what do we mean by that? We mean that, for example, let's look at n is equal to 2. The energy levels of the S is less than the energy level of the p-type orbitals. So if we look at another one further up, if we look at the quantum number n is equal to 3, so the 3s would have a lower energy than the 3p, and then the 3d would be higher. So it would be in that order, S, P, D, F. So S, P, D, and oh, here there's no F. But let's look at, for example, n is equal to 4. So here is your 4s, S, P, D, and F. And you can see that, for example, the F orbitals, their energy level is actually just below that of the 5d orbital, and just almost the same as the 6s orbital. So these energy levels of these orbitals really matter in the way the electrons occupy these orbitals. And keep in mind, each one of these orbitals gets 2 electrons, so that when you have the 1s orbital, that means you have 2 electrons there. When you have your 3p orbitals, like you have here, or here, or here, all of these 3p orbitals would have 6 electrons, 2, 4, 6. Your 5 of your d orbitals, so the d orbitals come in 5s, shown here with the green balls, each of them would get 2 electrons. The d orbitals would have collectively 10 electrons in them, 2, 4, 6, 8, 10, and so on and so forth for the f orbitals. F orbitals come in 7s. There are 7 of them, 2, 4, 6, 8, 10, 12, 14. So, and that this energy diagram of an atom is very directly related to the types of chemical properties and the position that the atom will have on the periodic table. And that's actually one thing I want you guys to do. You'll see it later on at the end of the lesson. That is part of your homework, is to look and see how do the chemical properties and the position of the elements on the periodic table how do they relate to its energy level of the orbitals. So if you were asked to draw an energy level diagram for any given atom, what are the rules? Okay, so there's it's hard to remember that, okay, 2s is here, 2p, and then when we get up here, oh, the 4s, and then the 3d, and then the 4p. It's hard to remember this arrangement, but it has to follow that energy order. So there's a little just a little memory tip, something to help you fill your energy level diagrams. This is called an off-bow diagram, and it's helpful for filling orbitals. And in an off-bow diagram, it's shown how electrons are added to each orbital, beginning with the 1s orbital at the bottom here, until no electrons remain all the way to the top. And you just follow the direction of the arrows. So first, you would put your electrons into the 1s orbital, then you would go on to occupy 2s orbitals. Then you go to occupy 2p orbitals, followed by 3s, followed by 3p, and then 4s, and then 3d, and then 4p, 5s. So you just follow the arrow here in this off-bow diagram, and this is how it's set up. And you can use this diagram to help with the drawing of energy level diagrams and work your way up to wherever you run out of your electrons. So here I have just a little picture of energy level diagram for lithium, carbon, and fluorine. And electron orbitals will have to be filled from the lowest energy level, so the 1s, n is equal to 1 would be the 1s, up. And we follow the off-bow principle. And the electrons go into the orbitals corresponding to the lowest energy level that's available. And keep in mind that each orbital can hold up to 2 electrons, and that the electrons in the same sublevel should not be paired up until all the orbitals in that sublevel have at least 1 electron. And this is called Hund's rule. So what do we mean by that? We mean that, so in lithium, for example, lithium has got atomic number 3. So it has 3 protons on the periodic table. It's number 3, which means it has 3 electrons. How do those electrons get filled up? Well, we start with 1s. 1s gets 2 electrons, 1 up, 1 down. We move to the next available energy shell. The off-bow diagram tells us that's 2s. And also we remember the next one after 1s is 2s. So the third one goes in there. Does it matter whether you draw the arrow pointing up and down when it's just 1 arrow? No, it doesn't matter. Pick one, either up or down. So here is energy level diagram for lithium. Do we put anything in the 2p? No, because we have only 3 electrons. 2 of them went into this energy level and 1 of them went here. Stop. Say for carbon now. For carbon, carbon is number 6. It has 6 electrons. So we start by putting 2 here, 2 into 1s, 2 into 2s. We're left with 2 electrons, which will carry up us to the next energy level, the next set of orbitals, which would be the 2p orbitals. And we have 3 of those. P orbitals come in 3s. And so do we put 2 of these electrons in the same 2p orbital? No, we don't. According to Hund's rule, we don't start pairing them up until at least every orbital in this sublevel has 1. So for carbon, we stop like this. For fluorine, let's say, fluorine has got 2, 4, 6, 8, 9 electrons. So we start with 1s, gets 2, 2s gets another 2. And then in the p orbitals now, we put 1, 1, and 1. And once we have 3 single electrons in each of the 3 p-type orbitals, Then we can go up and add one more and pair them up. And when we draw them, we make sure that they point in different directions. And this one doesn't get one because we don't have enough electrons to fill us up there. That would bring it to the next element on the periodic table. Any questions so far? Sorry, I've been talking nonstop and haven't really paused to ask if anybody has any questions. Are we following what I'm saying so far?
Yes.
Yes, okay, all right. So let me know, stop me at any point, interrupt me if you didn't understand something that I was saying, interrupt if you think something doesn't look right, ask me if you think you see a mistake on my slides on my presentation. Feel free to talk and interrupt. So yeah, maybe I'll ask somebody this question. Let me see if I can throw up this periodic table. Actually, we'll do that later. So let's look at maybe another example. So in this example, let's take a look at example of oxygen. So oxygen would be the element right before fluorine. So fluorine would have 9 electrons. Can anybody tell me if oxygen is the one right before fluorine, how many electrons would oxygen have? So if on the periodic table, oxygen comes right before fluorine, and if fluorine is number 9, and that means it has 9 protons and 9 electrons. If oxygen is the element right before fluorine, what number would oxygen be? What would be the atomic number for oxygen? And how many protons and electrons would oxygen have? Does anybody want to take a stab at that?
8.
8.
8, yes, thank you, 8. So looking at, for example, this energy level diagram, can someone talk me through then how would you go about filling up 8 electrons? Anybody want to take a stab at it, give it a try? There's no problem. You're allowed to make mistakes.
Sorry, I didn't hear well. Can you say?
Yeah, does anybody want to try doing this kind of a diagram with oxygen? So you can just talk me through it. So oxygen would have how many electrons?
Say the first one on S1 is going to be 2.
Yes.
And the second one is going to be 2 again.
Yeah.
And then on 2p is going to be each one 1. And then there's going to be 4 and then 4 left. So the first one going to have 2, the rest only 1.
Right. And just make sure that the one that has 2 has got the arrows that represent the electron spins are in opposite directions, 1 up, 1 down. Yeah, exactly. I just wanted to see if we were following along before I went to the example and gave you the answer. So yeah, exactly. So first you would do 2 in the 1s, 2 in the 2s, and then you would start by putting in 3, 1 each in of the 2p orbitals, and you still have 1 more, and then that last one would get paired up, making sure that we represent them as having opposite spins. And then you have your energy level diagrams. And there's many alternate ways of drawing these energy level diagrams. This is one way. This is another way. You can start with 1s at the bottom and work your way up, or you can start with 1s at the top and work your way down. There's other ways of doing it here. You can even do them this way with squares. You could do them, this is another way. Just draw lines and spin up, spin down. like that. So these are all correct. This one, yeah, I'm not sure so much, but anyways, all of these are ones that are used. Probably this one in the middle and maybe this one are the most common, typically used, just because they look so simple and so easy. You can also do it this way. So let's look at, yeah. So what if you were doing it for nitrogen, but you're asked to do an energy diagram for not just the nitrogen atom, but for a nitrogen anion. So it has a charge. It has a charge of -3. It's an N-3. What would you do there? So I've kind of taken you through it, the example here. So keep in mind that nitrogen, if you look on the periodic table, and oh, I wish I had put a periodic table here on one of the slides that we could look at, but yeah, maybe I can just quickly grab one here. I'm not sure why I'm having trouble sharing this screen. Ah, here we go. All right, so yeah, this is one page of this book that shows right. Can everybody see that? Can everybody
Yes, I can
see
see.
that periodic table? Okay, just wanted to make sure I shared that correctly. Okay, so right, so here's the periodic table. And so if you look at nitrogen, you can see that nitrogen is number 7. So it has 7 protons, and it means that it has also 7 electrons. Let's go back to our slide. But if it's an N-3 anion, what does that mean? That means it has 7 electrons, plus it has 3 more electrons. It's a negatively charged ion. So altogether, we have 10 electrons to deal with in our energy level diagram. So if we were to fill up for nitrogen, this is where we would stop. We would stop at our 2p orbitals, the 3 of them, each having a single electron. But because this is a nitrogen anion and it has 3 extra electrons in there, we go ahead and fill in those 3 extra electrons, and this is what it looks like for an anion. Is that clear to everybody?
Yes.
And if it was a cation, if it had a plus charge, that would mean it would be missing some electrons, and you would also deal with that accordingly. Right, so there's like a little procedure which I basically have here. It's the same thing that I talked you through about how do you go about writing these electron configurations. So these electron configurations are basically shorthand form for what you see here in these energy diagrams. It shows that you have 1s2, 2s2, 2p3 here. So we have 1s with 2 electrons, 2s with 2 electrons. You have 2p with 3 electrons. And for the nitrogen anion, it would be 2p with 6 electrons, because each of them would have 2 in them. So yeah, these are called electron configurations here. And electron configurations just give you a description of the arrangement of the electrons, the distribution of the electrons in the various orbitals in increasing energy level. So for example, if you in an electron configuration, you see 1s2 or 1s squared, the 1, you know, is indicating the n is equal to 1 energy level. The s, you know, it means that the electrons are in the s subshell, where the value of L is equal to 0. And the 2 here indicates how many electrons are in that subshell. And in this case, it's 2 electrons, because S subshells always get just 2 electrons. So here, for example, oxygen atom would be 1s2, 2s2, and 2p2. We looked at oxygen up here. Oh, no, 2p4, sorry, that is a typo. 2p4. So couple of examples here to go through. You can go through them yourselves later on to convince yourself that this is correct. Write the electron configuration of sodium atom. So sodium atom with the electron configuration would be this. For a fluorine ion, so anytime it has ion, pay attention to the number of electrons would not be what you would find on your periodic table, because you're looking at the ion. And so, yeah, go ahead and do these on your own to make sure they're correct. If I've made any mistakes, please feel free to help me correct them. Then there's the shorthand form of these electron configurations. And in the shorthand form, you have this abbreviated writing that uses your nearest noble gas on your periodic table. So for example, if you have chlorine, and chlorine is written like this, in the shorthand form, you can use the nearest noble gas, which is neon. So let me take you back to that periodic table. So chlorine is right here, number 17. And the nearest neon gas, the nearest inert gas would be neon up here. So you would use that and then fill in the rest of this information. So it would look something like, neon. And then so this part would be dealing with neon. And then you would use the rest here. And that would indicate to you that it's chlorine. For SN, for tin, you would use, let's go back to the periodic table. Yeah. So where is SN? Here, number 50. So you would use chromium up here, and then you would fill in the rest to bring you up to SN. And it would look something like this. So up to this point, up to your 5s2 would be chromium, and then you would fill in the rest. So that would be a shorthand notation. So again, I wanted to give you a pictorial reminder of how to apply Hund's rule properly. And, oh, it seems like we lost someone here. So in Hund's rule, just remember that you can't fill in your orbitals in this way. It's incorrect, and this would be the correct way of doing it. It doesn't matter if this arrow is pointing up and down, as long as it's the only one in there by itself, but this is incorrect, this is correct. And we already discussed that there are alternate ways of drawing these energy level diagrams, and they are all correct. You have some support questions here to help you understand the concepts in these lessons. And finally, you have some key questions. These key questions are due on this Sunday, September 19th. I will accept questions that are handed in by Sunday midnight. Anything submitted after Sunday midnight, I will not grade, I will not mark. So make an effort of submitting in your question by the deadline of Sunday, September 19th, by midnight, preferably sooner before that. So these are the questions, and I sent you guys a PDF file. Oh, hang on, let me just admit Borna. I think he dropped out. Borna, I think you cut out there for a little bit.
Yeah, my laptop ran out of battery, sorry.
Oh, that's okay. So I was just mentioning that there's some key questions, some support questions here for you guys to practice with. And that here are the key questions, the second set of key questions that are due Sunday, September 19th. And my cutoff deadline for accepting any homework submissions is Sunday midnight. So get your assignments in before Sunday, definitely no later than by Sunday midnight. Anything after Sunday midnight, I just cannot be bothered to go back and retrieve and mark with. At Sunday midnight, I go into the Dropbox, I grab all the assignments that are there and I start marking that. And after that, I don't look at it again. After that, I'm done. So please make sure to get in your assignments by Sunday midnight. If you have a very, very valid reason why you might not be able to hand it in, why you might need an extension, talk to me before your before the due date and before it's already late. You should have an idea already if you know that you have something pressing, something urgent, something important, and that you are not going to be able to hand in your assignment by time. Get in touch with me, email me, and explain to me your very valid reason. Otherwise, assignments are due Sunday midnight. Anything after that, I won't be marked. So when I emailed you guys a PDF file that had like lesson notes for unit 1, lessons 1 through 1, 2, 3, and 4, one of the key questions I changed, and I've highlighted that in here in 5. So if you are referring to those PDF notes, just keep in mind that question number 5 is different. The original question had you creating a pamphlet that had to do with lasers. I think I would much rather have you go through this exercise. I think it would be much more useful in covering the topics that we've discussed here in today's lesson, to list the characteristics on the periodic element table of elements of the S, P, D, and F blocks, and explain their relationships between the position of the elements on the periodic table, their properties, and their electron configurations. By that, I mean, take a look at your periodic table. So here you have the S, P, and D blocks. This would be like the S block. This would be the D block. This would be the P block over here. So, and really look at it and analyze and understand how these elements are grouped, the behavior, the properties. This is also kind of touched on that periodic table diagnostic. I want to see if you guys understand how the different areas of the periodic table, how their properties of the elements are related together. So how are the elements that are in this 1A group, for example, similar? What do we call the elements in this 2A group? How are they similar? How about these elements down here? What are they and how are they similar? And how does that relate to their electronic configuration? So that would be an extremely useful exercise. And that's why I've included that as the final question for your homework. So I just had some extra notes, but I think I already talked about these during the bulk of the lesson. Once again, I will be posting these and sharing these with you through Google Drive. Now tell me, did everybody, was everybody able to access the things that I shared with you on Google Drive? Did everybody try and access those and was everybody successful?
Yes, I did.
Yes, Sasan did. Okay, how about Borna?
Yeah.
Yep, and Judy, were you okay to access those material on Google Drive?
Yes.
Yes, perfect. Okay. Last semester, some students had some trouble. A few actually never seemed to have bothered to go into the Google Drive and look for this material until it was really way too late to be looking at this. Some of them were looking at this when it was time for midterms, which is really way too late. All this information is shared with you, made available to you through the Google Drive. I will post this lesson also. I will email you the link for the cloud recording of this lecture. So feel free to go through it and look at it, and you can use my slides to help you enrich your notes, those Unit 1 notes that I sent you. I find that those are very sparse, and that the material that I have here in my lectures here really help to enrich your understanding. I hope you find it that way. And if you have any questions about any of the stuff that we talked about here today, feel free, contact me, email me, look in your textbook. Your textbook is an excellent reference source. You can also go ahead and look for things on the internet. However, I strongly recommend, as you should know with anything that you look up on the internet, do not take the first answer that you find on the first site that you refer to. Look at a few sites and make sure that whoever has posted that information has got it right, and that if you are referring to the internet to understand some of these concepts and topics. There's so much available out there. You just have to make sure that what's out there is valid. But your textbook is really such a great resource. Any questions? Anything that I can take up with you? So next class, we'll be doing lesson 3, and also, we will be doing question number 1 of that Borna will be answering for us at the beginning of the next lesson. Okay?
Yeah.
Yeah, perfect. All right. We can, any questions on the material covered here, the quantum mechanics?
No question.
No questions. Okay, perfect. In that case, I can wish you guys have a good evening, and I'll see you next Monday. Make sure to hand in your, oh, sorry, one more thing. The way I like to collect assignments is through Dropbox, and I'll email you the links to the Dropbox. So make sure you use the correct Dropbox for the corresponding assignment. I will send you the Dropbox links for all the different assignments that you have to hand in. So make sure this assignment number 2, you use the link for assignment number 2 when you're putting it in the Dropbox. I really prefer that everybody convert their work into a PDF file, and that instead of handing me single sheets of JPEGs and 5 different JPEGs that I have to collate together that correspond to your 5 different questions, put it all together, one PDF file that contains all the questions relevant to that assignment, please, and deposit it into the Dropbox. Make sure your answers are written clearly and legibly. Otherwise, it's going to be very hard for me to understand what you've written, and I might not be able to give you the full marks that you deserve for having done your work. Okay, any questions about that? Okay, all right. In that case, I'll see you next Monday. Same time, 6 p.m. All right.
Yes.
Have a good evening.
Have a good day. Thank you.
Thank you. Bye-bye.
Bye.
Bye.